A continuación, Sebastien Valade nos va a presentar el trabajo Investigating Pre- and Seen Eruptive Dynamics from Satellite and Ground-Based Sensors. Adelante, por favor, Sebastien. En inglés, ¿verdad?
Sí, en inglés, verdad. Yes, my Spanish is unfortunately rusty, so I will do the presentation in Spanish, in English, I'm sorry. So thank you, first of all, for having me here in this Seminario. I would like to present this talk, my main research, which is about investigating pre- and syn-eruptive dynamics from satellite and ground-based sensors. So before I go into the details of the talk, I would like to give an overview of the goals and rationale and methods of my main research interests. So the main goal is to better understand eruptive dynamics, and this includes both pre-eruptive precursors and syn-eruptive dynamics, both on effusive and explosive volcanic dynamics. Now, the rationale behind this is twofold. It's driven by two main concerns. One is a scientific one, to try to deepen our knowledge of the volcanical processes at stake at volcanoes. And the second one is to produce more successful eruption forecasts in order to better mitigate volcanic hazards and risks. Now, the key to do this is actually to recognize when a volcano is deviating from its background level of activity. And in order to do this, we have to do monitoring. And what is monitoring? It's basically observing the activity of the volcano during various regimes, both quiescent, phases of unrest, and eruptive regimes. And my method is mainly trying to integrate different types of sensors, namely satellite-based sensors and ground-based sensors, in order to try to understand the eruptive processes which are at stake at various spatial and temporal scales. Now, this leads me to my presentation outline. In the first part, I will talk about satellite-based observations, and I will show you that in recent years there are new generations of satellites which allow a comprehensive understanding and observation of the volcano. And also, since the data is free, it gives us a great opportunity to investigate various types of dynamics. And so, in the first step, I will briefly talk about the achievements of the monitoring platform which have been developed in the past 2 years and the future directions. And in particular, within these directions, I would like to investigate the applications to understanding volcano domes, and in particular with the case of Popocatépetl. I will show that I would like to tackle the possibility to track cycles of dome destruction and construction with SAR images, and couple this then with an analysis of multi-parametric data sets to try and understand the life and death, so to say, of a volcanic dome. I will then briefly talk about ground-based observations, because these are fundamental to capture phenomena occurring on shorter timescales and which require a higher level of precision. And this is actually a key point where I think that it will be very fruitful to have close interactions and collaborations with all of the team members. And last, I will very briefly mention a project which is dear to me, which is about the development of a sort of rapid response task force, so to say. But because this is actually very technical and also very linked to political decisions, I will be very short on this. Now, let me start with the satellite observations. Basically, as I told you, in the recent years, since 2014 roughly, the European Spatial Agency has launched a series of new Earth-observing satellites. And these are called the Sentinel, and they are 7, or at least 7 are planned. And importantly, on board these satellites, these Sentinel satellites, there are different sensors which range with different wavelengths within the electromagnetic spectrum. And this variety of sensors actually provides us the possibility to have a comprehensive observation of the volcanic phenomena in various volcanical contexts. In particular, the Sentinel-1 that you see on top is a radar, has on board a radar, synthetic aperture radar, which I will call in the next of the presentation SAR, and this will be actually key to the rest of the presentation. The Sentinel-2, on the other hand, I have multispectral instruments through which we can observe the heat in particular, which is radiating from the volcano. Sentinel-3 is another type of sensor with a bit longer wavelengths with thermal infrared, which allows us to track potentially ash plumes. And last but not least, the Sentinel-5 has on board UV sensors and actually provides values of SO2 within the atmosphere. And so this was basically the core idea of what I've been developing in the past 3 years, to use open source data, so Sentinel-1, 2, 5, and also free earthquakes catalogs, to try and observe various eruptive processes and provide a monitoring platform which can enhance our understanding of these processes. So the project is called Mounts, and basically range from the download to the processing to the web publication of the datasets over a number of volcanoes worldwide. And there is now a publication which I have just recently submitted, and I have had a minor revision, so it should be out in a very short moment, which is entitled Towards Global Volcano Monitoring Using Multi-Sensor Sentinel Missions and Artificial Intelligence. So what processes can we actually observe? What volcanological processes can we observe? Well, with the Sentinel-1, we can, thanks to interferometry, look at inflation prior to the eruptive onset. And during the eruptive onset, we can observe dike intrusions or strong deformations, for instance. This is what I flagged with an asterisk here. I don't know if you can see the cursor. Here, dike intrusions. So this is a case that I have presented in the paper, which is on Piton-La-Forez, most precisely. And during the eruptive event and post-eruptive event, we can look at deflation. We can also use Sentinel-1 data to monitor edifice building or edifice destruction, as I have showed with the Krakatau in 2018 eruption and Kilauea 2018 eruption, and I will give you a small presentation of this in the coming slides. Importantly, also, we have the possibility to look at the surface changes, and so with this we can look before the onset of an eruption. We can observe high summit activity, for instance, but also during the eruptive activity itself, we can look at the emplacement of deposits. And in particular, I showed this with the case of Ertaale, so in a very desertic area, but also at Fuego, so in Guatemala, in a very tropical region and completely different volcanic context. Sentinel-2 provides the possibility to, as I said, track heat anomalies, and in particular track lava flows, for instance. Sentinel-3 can track ash emission. Sentinel-5 can track degassing, so UV and SO2 in particular, which is being emitted by the volcano both prior to the eruption onset and during the prior onset. And last but not least, there are also, in certain cases, the use of global earthquake catalogs provided, for example, by USGS or Geofon, can provide information on the deep seismicity which can precede an eruption, and this has been in particular useful to decrypt the Ambrim eruption in the last year. So as you can see, this interdisciplinary approach allows us for assessment of a variety of volcanic phenomena in various volcanological contexts. Now, unfortunately, I don't have the time to talk about all of these, but I would like to use what has been built to apply to Popocatépetl and Colima and the volcano domes that are hosted in these two volcanoes. So this is the website, the main page of my website, and Popocatépetl and Colima are already monitored since a few months, not so much, but the data is started being collected, and we can already look at various features. But importantly, what I would like to do and what I think can be very innovative is to try to decrypt the cycles of dome destruction and destruction with satellite observation and SAR in particular. So what is a SAR image? Well, a SAR image is first of all an active remote sensing technique, which means that the sensor on board the satellite sends an electromagnetic wave, which due to its wavelength is able to penetrate through clouds. And so this is actually provides a very high potential for volcano process tracking, and in particular tracking of morphological changes. I would like to give you a very short example of this using the recent example at the recent eruption at Kilauea in 2018. So on the top row you see on the top row you see the SAR image. On the top left, it was before the eruption, so you can see here a shadow which corresponds to the active lava lake, which is imprinted on the infrared images as a hotspot. And after the eruption, there is a drainage of the lava lake, and there's the entire crater which collapses. And as it collapses, it actually deposits ash and crushed products, which you can also see on the SAR. Now, this process occurs during several months, and as you can see in this video, there is the progressive deepening of the entire crater terrace. So this is a very wide collapse. It's about 3 kilometers wide. So it's very impressive. It's very obvious that we can detect this from space. But now this was to show you that through this technique we can perhaps decipher the changes in the morphology in, for example, the Popocatépetl volcano. So the most straightforward approach would be to track shadow regions within these satellite images. As you can see in this picture here, the shadow region will inform you on what is being constructed or destructed, depending on whether this shadow region increases or decreases. As a matter of example, Barrière et al. Recently showed that they can apply this to track lava lake level monitoring, but I think a very similar approach can be used with domes such as at Popocatépetl. Now, I have done a very preliminary test, and these are 3 images at Popocatépetl from October of last year to February of this year. And if we zoom in and do a bit of processing, I highlight here in red the shadow area which I was talking to you about. And we can see that basically this area decreases, and which could correspond potentially to a crater filling or a dome building episode. So this is something that I would like to continue to investigate. This technique, however, may suffer from artifacts. It may be also very difficult to generalize to other volcanoes due to various particularities of the morphology. So I would like to, in fact, investigate another very innovative approach, which I have started to tackle, and it's to use the artificial intelligence. Now, why? Because in this recent paper that has been published, we have actually used artificial intelligence, in particular convolutional neural networks, to generate synthetic data sets. So these are interferograms, so they show you deformation. And we have trained these to output the phase gradients, which corresponds to the deformation itself. And then this was then directly incorporated to automatically detect these strong gradients. And this is, for example, a dike intrusion at Piton de la Fournaise. And we have showed that this works very well. It's very robust. And so the idea is to try to apply something similar, but to try to decipher the presence of these volcanic domes. First, we would have to generate SAR images, both in ascending and descending track, and train a network to recover basically the morphology. So create different data sets and generate the radar image and train this network. And in turn, once this network is trained, hope that by feeding it some incoming SAR images, we can recover morphological changes, in particular differences in the deepening or the construction of the crater, etc. Another key point that I would like to investigate in my research is to compare these potentially the construction destruction cycles that I hope to recover with other types of data which I already collect. So, for example, as I told you, on the top row here, you have the analysis of the infrared images which are provided by the Sentinel-2 satellite. And on the bottom row, on the other hand, is the SO2 mass, which is outputted. Again, this is the example of Popocatépetl. And you can see that already in a few months, we can notice some oscillation. So we cannot talk about cycles yet, but my hope is that we can continue accumulating, collecting this data to actually recover what is going on. So this is an open question. Can we decrypt the activity or the cycles with multi-parametric datasets? And to try to answer the questions of what the main controlling factors are for dome growth and destruction. This will be, of course, key to compare with the ground-based observations that we have at our disposal. And on this, I think it will be a key point where it will be a very interesting opportunity to exchange and to learn from the knowledge that is in the group. So first of all, there is the work being done with Doppler radar in your institute, and Doppler radar, ground-based Doppler radar, is actually something that I have worked with during my master. I actually worked on the Doppler radar at Popocatépetl and started to work on this, and more intensively during my PhD, I looked at the ash generation mechanisms and the combinations with seismic and acoustic signal at not specifically lava dome, but let's say explosive settings. So I think that here it will be very interesting to work with this data and to incorporate it to the rest of the data to see what it can tell us. A second point. In your institute, and a very interesting paper came out by Robin Campion, which was using in particular UV cameras to decipher the degassing mechanisms at lava domes. And I have worked a lot with video images, and I would be very keen on collaborating to combine this additional information to the general understanding of the lava domes. Last but not least, many of you are working, so of course this list of people that I present is not exhaustive. Many of you are working with either seismic or acoustic or both sensors, and I have also worked with these a little bit, and there are many things we can learn from this, in particular how the energy is partitioned within the atmosphere and within the ground, and in turn what it tells us about the eruptive mechanisms which are occurring at the subsurface. So this is something that I would be very happy to collaborate with, and I think you have a lot of knowledge, and I would learn a lot from this. Last but not least, as I said, a project which is dear to me is the possibility to develop a rapid response task force. And the idea behind this is actually to capture the processes that state during the very early stages of an eruption. And this in particular would be interesting from a scientific point of view, again, of course, but also very useful in many settings for hazard mitigations, as many volcanoes sometimes do not have a proper network, and it would be interesting to provide this in a fast way. So this requires very rapid field deployments, and for this we need to be very organized, and the idea would be to develop a mobile laboratory. This would be very interesting to work on this topic with other members of the group, which have a lot of experience in the field. And okay, these are a few images of basically a toolkit of what should be inside this and how it should be structured. But I will not go into much details about this, as this is, as I said, something very technical and also very much linked to political decisions. So I will be happy to discuss about this, but I won't go into the details here. This leads me to my conclusion slide. As I said, my main interest is to better understand eruptive mechanisms, both from pre-eruptive precursors to syn-eruptive dynamics. I'm very interested in both effusive and explosive dynamics, and using in particular both satellite-based and ground-based sensors. I would, however, like to, in the coming years, to focus more specifically on volcanic domes, in particular at Popocatépetl, since it's a neighbor. And with, in particular, as a first point, the development of novel methods to try to decrypt, decipher the construction and destruction cycles of these of volcanic domes and the crater terrace in general. And this, I suggest to approach it with SAR imagery and also artificial intelligence, and in particular machine learning with convolutional neural networks. Last but not least, all of this collected data is to be analyzed, compared, and I hope that it can deliver more deeper look into the both long-term and short-term processes at dome hosting volcanoes. And I think that here will be a key point to interact with the group members, both from geophysics, but also from more volcanology background. And I think this will be very fruitful. So thank you very much. Oh, I am early.
Thank you, Sebastien. There are going to be some questions from here. Just a minute.
Yes.
Yeah. Hello, Sebastien. Do you feel comfortable
Hello?
if I ask the question in Spanish? You can answer in English, or you want me to speak in English?
Since I see your English is very good, I would prefer English.
Okay. Okay, so I'm not very familiar with these things about satellites, so I just wonder how much do we depend on this Sentinel program, on these satellites? I mean, who is the owner of these satellites? Who is the funding for these satellites? And what will happen if funding is cut? I mean, what will you do in that case?
Yes, good question. Of course, if there is a change in the policy, but I doubt it is, because there's massive funding from the European Spatial Agency. All of these data are free, and this is really the new trend, to have open source data, open source software, and so I really strongly think that the policy should not change. So the underlying also question is that the software or the monitoring system which I have developed is actually running on one single computer, and it doesn't cost anything. So this is an opportunity, as I said, because this data is free to use for the moment, and we should really seize the opportunity. Yeah.
Sí. Ana Lilian Martin.
Gracias. Well, I think my question has a little bit to do with the question that Giovanni made, because especially with this last point where you had this this rapid task force, you have to consider that a lot of this information, we've worked for many years with a lot of people from Senapred in here, and one of the main problems with this is that there have been less budget for science, so you have to be very conscious of the limitations that we have with this. What would you do to try to get this going? And you have to consider also that Senapred is the actual monitor of the volcano, and we work with them most of the time.
Okay, so I think so the interaction with Senapred, I'm not sure how to answer this directly. I've always been within a university background and collaborating with agencies which are in charge of the monitoring. So my experience in in Italy, for example, has been really collaboration. It's not a matter of taking over SENAPRED, and this is absolutely not our role as university members, but rather to apply our research and to monitoring. And I think the products are rather to be used or shared, but they're not meant absolutely to overcome or a step on SENAPRED's feet. So I'm not sure if I replied to this specific concern about the SENAPRED. Regarding the second point of your question, is how to deal with the fact that there is maybe less money going into science in particular. What I would like to do in the coming months is actually to write proposal with the European Space Agency to actually have a foot inside their system and to try to have recurrent funding. And the reason for this is that it's strongly pushed by international organizations, both in Europe but also in America and North America, to try to integrate these data and to try to pull together things and make something useful out of these products which are set free. So I know there are a number of funding opportunities with ESA, and my wish is to try to apply to these things as soon as possible.
Okay, Roberto Carniel. Sí.
Sí, I have several questions actually. One is very, very short. So the data that you use as input is open. Is also your software open and your results open?
So yes, absolutely. The software which I use is actually an open or at least free software, which is delivered by ESA as well. So it's meant to go together with their products. So this is the first point. The second point is that yes, my research algorithms are on GitHub, or soon will be, as I am now ready to submit the final revisions of the paper. So the algorithms are open source as well, and the results are, of course, the website is completely free of access, and it's already being used by some members. For example, there is the Ecuadorian colleagues which are now using the system to look at Sangay volcano, which is in a very remote place, so they don't have many ground-based stations. So I actually interact with them and to provide specific products. In particular, they're interested in infrared products. So yes, the idea is really to keep everything as open as possible.
Okay, thank you. And then you mentioned the generative adversarial network, but I did not get why or how you plan to use them.
Mm-hmm. So the genetic adversarial network, in this presentation, I didn't mention the genetic adversarial network precisely. It was more convolutional networks in general. The genetic adversarial network, we have used this in a recent study in which we actually used this okay, maybe I'm going to so yes, I will first answer to how we use the guns. I'm sorry. So the guns were used to basically generate, transform Sentinel-1 image, so radar image, into a Sentinel-2 image. So to transcode basically from radar to optical. So the gun has to learn how to transform from one to the other. And in doing so, it is forced to recognize a different feature. And so by adding a few labels, we can actually, in a very fast and robust manner, do some land mapping, so to say. And the idea was to use this for volcano deposits as well. So this is a paper which has been recently published. But in this presentation, which I discussed, the idea is more to use autoencoders or convolutional networks, so not the generative adversarial network, which have basically a UNet and a second network aside. Now, why use it? The idea is actually to, so to say, it's a sort of PCA of machine learning, so principal component analysis of machine learning. So we're trying to extract the maximum of information of our data, and it has been successful with this detection of ground-based deformation. No, I'm sorry. It has been successful with the detection of ground deformation from the interferogram, and so the hope is that we can build a similar system to recover the changes in the topography or in the morphology of the crater.
Mm-hmm. And regarding convolutional neural network, how many data do you need for training, and how much does it take? I mean, because I guess that afterwards you could use it just almost real time. It's not so computational intensive. But what about the training? Is it but is it unsupervised or supervised training?
So the training is in fact done because we have this main issue that these networks actually need a lot of training data. We decided to bypass this by creating synthetic data sets. So in this case, our limiting factor is to try to create synthetic data sets which are as close as possible as our images. And when we have created this, then we have no limits of how much data we can generate. And also the second advantage of creating synthetic data set is that we no longer need the ground truth because it's incorporated into our synthetic data set. So maybe I can go back to the slide very shortly. Can you see my screen or no? Share screen.
Not yet.
Oh, yeah.
Okay. Now?
Yes.
Okay. Yes, sorry. Okay, so this is what is being used now in real time, in fact. So this first part on top was the training. So as you see here, this is a synthetic interferogram, so generating a fake deformation, ground deformation. And this was computed basically based on the gradients that we give it. So we train this network to recognize by having this input to retrieve this output, but it was actually used to build this. So this is the way that we train our network. And then once this is trained, this is actually just a function, and this is now implemented into the system. And as soon as an interferogram is generated, it goes through this network. So it's fed through this network, and it outputs the exact same products on which we have trained it on. So the phase gradients and a noise mask. And so the idea is to kind of do the same thing with a slightly different approach. We would generate synthetic SAR images from ascending and descending tracks. So we're looking on two sides of the volcano, and this would be generated based on realistic topographic changes, so deep crater and crater filling, etc. So this is the main idea. I don't know if I was clear.
Right. How long does it take?
I can talk only about this because the other this is work will have to be done. But the training could take maybe I don't know. I did this with my colleague, so he was mainly in charge of this. Maybe something like a night, overnight, and then once it's trained, the resolution of this, even for very large interferograms, it's a matter of seconds, even less than a second.
Yeah. Okay, thank you.
Thank you.
Muy bien. Marco Calo.
Hello, Sebastien. Can you hear me?
Yes, I can hear you.
Yes, thank you for your presentation. Anyway, quite really clear, and you gave an idea of the global impact that can have your investigation anyway, and also thank you if you want to focus more in the Mexico volcanoes, and I'm not concerned about the policy of satellite in the future because I think that this is the future anyway. But I would like to make a question about your integration of ground-based data and remote sensing data. No, then For example, how do you think manage, for example, deformation data? Here, for example, in the Popocatépetl, we start having a network of GPS that could be integrated in your database. How do you think develop this kind of integration that will be really interesting, okay, to compensate remote sensing and ground-based data?
Okay, so from a practical point of view, whichever the sensor type on ground-based, it will be very easy, I think, to populate common databases with common time parameters and values. So to visualize these will be very easy from a practical point of view. From how feasible this is, it really depends, I think, on the type of data that we're going to incorporate. And I think that the deformation will be, in fact, one of the most difficult ones. The reason for this is that, for example, it is well known that many open conduit volcanoes, such as Popocatépetl, but also Colima. There was a recent paper by Philippe Lesage on this, about the 2015 eruption at Colima, during which there was no clear detectable precursory deformation prior to a very large eruption that occurred, and the reason for this is that it's an open system, and so there is not necessarily a sort of pressure accumulation which leads to deformation. So on the deformation, it's a very tricky question on which it will require a lot of thinking. However, other parameters might be much easier to incorporate. For example, the ground-based Doppler radar. We can easily output a value which can be ideally would be the mass of ash which is detected by the ground-based Doppler radar, but it can be even lower level information such as the backscattered power. And by comparing this with, for example, the gas flux or the satellite-based SO2 mass recovered, we can have a look at the link between phases of ash emission and phases of stronger gas emission. Do they go together? Are they distinct? Are they decoupled or are they coupled? So I think that this will be easier to approach, and from a practical point of view, rather easy. It's just a matter of managing managing databases, basically.